Let's start out reviewing some basic trigonometry. If I define the sine of theta to be u over a, recall that we also defined the sine of an angle as the opposite side divided by the hypotenuse. So labeling this first triangle, I would have the u here and the a here. Using the Pythagorean theorem to get the missing side would be the square root of a squared minus u squared. Let's look at the second triangle using the tangent, and remember it was opposite over adjacent. And again, using the Pythagorean theorem to find the hypotenuse, this would be the square root of a squared plus u squared. And then the last one, I'm going to choose secant, and remember it is hypotenuse over adjacent. And the third side would be the square root of u squared minus a squared. Hopefully these look somewhat familiar. You should be thinking, I've seen some of these types of things before. In fact, when we reviewed our basic integration rules, we looked at our inverse trig functions and how we integrated those. And I want you to look here. That square root, the square root of a squared minus u squared, went with your arc sine. A squared plus u squared went with your arc tan. And the square root of u squared minus a squared went with arc secant. Hopefully you can see the similarities between these and these triangles. So we have the sine of theta with that square root, the tangent of theta. Now yes, the arctan didn't have a square root, just trying to show the similarities. We do have an a squared plus u squared, and your secant has the square root of u squared minus a squared. So when do we need to use trig substitution? Looking at this problem, the first decision you need to make is, what does it kind of look like? Does it look kind of like an inverse trig function? Yes, it does, but it doesn't quite fit the inverse trig rule, because if I have a plus, that would be arctan, but the arctan doesn't have a square root. But it looks kind of like arctan, so that means I'm going to choose this triangle. That means I'm going to choose the tangent of theta to be u over a. So a is 1 and u is 3x, taking the square root. So that would be 3x goes here, 1 goes here, and then we have a squared plus u squared. So the game that we're going to play is we're going to say, what can I make substitutions for? So I need to know what dx equals to, and I need to know what that square root equals to in terms of theta. So looking at tangent of theta, I know that's 3x over 1, if you will. Since I need the derivative, I'm going to take the derivative. And now I'm going to look and say, well, what do I have? I now know what 3 dx is. It's equal to secant squared theta d theta. So the only other thing I need to know is what's that square root. And this is where you look at your triangle, right? This side right here is the hypotenuse, and it has that square root that I need. So you're going to choose this side, and then you're going to choose the side without the variable. Choose the side without the variable. Then look at those two sides and say, what trig function involves hypotenuse and adjacent? So yes, you could go with cosine, but you could also go with secant, and since I already have some secants, that's what I'm going to go for. So the secant of theta is the hypotenuse over adjacent. So I'm going to erase some of my squiggly stuff, and then look and say, all right, I have 3 dx, and I also have the square root of 1 plus 9 squared. And so now I am ready to make my trig substitution. So this integral becomes, instead of 3 dx, secant squared theta d theta, that's important, the square root. Now, a lot of students get confused because, well, it's on the bottom. We're just substituting. We're leaving it on the bottom. And what does the square root of 1 plus 9x squared equal to? It equals to just the secant of theta. At this point, it's kind of nice that it probably will reduce. And in this case, it does. Just dividing secant squared by secant. And now we have an integral that we know how to integrate. The integral of secant is the natural log of the absolute value of secant theta plus tangent theta. We can't stop there because my original problem was in terms of x. So I have to go find out what is the secant of theta equal to. Well, I have it right there on my paper. It's equal to the square root of 1 plus 9x squared. I need to know what tangent theta equals to. I have that on my paper right there. It's 3x. And we're done. This problem, it's kind of like an arc sine in that it's in the form of the square root of a squared minus u squared, but not quite arc sine because that would be in the denominator for arc sine. But that does tell me I'm going to use the sine of theta. So the sine of theta being opposite over hypotenuse. So a is 1 and u is 3x. So opposite over hypotenuse. Then label the missing side using the Pythagorean theorem. Remember, a squared plus b squared equals c squared, rearranging, and you're going to get 1 minus 9x squared. Okay. So we have the sine of theta is u over a. Again, I'm going to need that dx, so I need to find the derivative, and the derivative of the sine is cosine. Now I'm looking here, in the previous problem I kept that 3 because I had 3 dx, but I don't have 3 dx, so I need to divide both sides just to solve for dx. The only other part I need is the square root. So I go to my triangle and I go, okay, that side has that square root. Then I pick the other side that doesn't have a variable. And I say, what trig function involves hypotenuse and adjacent? So yes, I could use secant like I did last time, but I have sines and cosines this time, so I'm going to choose cosine. So from the triangle, I know cosine is adjacent over hypotenuse. So I know this is equal to cosine, and I know my dx is equal to 1/3 cosine theta d theta. Now I can make my substitutions. So my square root is cosine theta. My dx is 1/3 cosine theta d theta. So bringing out the constant in front, I have cosine squared theta d theta. This is where we get to use that half-angle formula that we reviewed in class. So remember, cosine squared is 1 plus cosine 2 theta over 2. So bringing that 2 outside, so I have 1/6 of 1 plus cosine 2 theta. So now integrating, I have 1/6 theta plus 1/6, then integrating cosine 2 theta, I have 1/2, because of the 2, sine 2 theta plus c. But I still have to go back and put it in terms of x. We have some work to do. All right? We have the sine of theta, but I have here 2 theta. And no, you can't just double it. So how do I get there? Well, I need to go back to some trigonometry and say, hey, I have this identity that the sine of 2 theta is 2 cosine theta sine theta. I'm going to keep going even though I'm slightly out of room on my paper. I have 1/6 theta. I'm going to make that 1/12, and then I'm going to replace the sine of 2 theta with this identity. And then I'm going to reduce the fraction. 2/12 again is 1/6. Still not done. All right, so on my paper, I know what cosine theta equals to. It's the square root of 1 plus 9x squared. I know what sine theta equals to. It's 3x. But what the heck is theta? Well, it's many things. You can call it many, many things, right? So I can look up here and say, hey, I have cosine theta. How can I get theta by itself? Well, I could take the inverse cosine of both sides. So one option is I could say, hey, theta equals the inverse cosine of the square root of 1 minus 9x squared. And that would be okay. I could also go right here and say, hey, theta equals the inverse sine of 3x. I could choose lots of different trig functions in terms of theta. I think I'm going to choose this one just because it's a little bit, I don't know, prettier than that one. Right, so to finish up my problem is, so theta, one option is to put it as 1/6 times the inverse sine of 3x, and then cosine of theta is the square root of 1 plus 9x squared, and the sine of theta is 3x. And I guess you could go and reduce the 3 and the 6, but you know what? I think I'm just going to stop. It looks good.